So today we're going to talk about logarithmic functions. Okay? On Friday we did inverses. So inverses of linear models are really easy. We switch x and y and we solve for y. When we are talking about exponential models, though, to find the inverses, it's a little bit tougher. And so the inverse of an exponential model isn't another exponential model like it is with linear. It is what's called logarithmics. Okay? So an exponential function, when we take the inverse of that, we're actually going to get a logarithmic function. And the first thing we're going to do is just look at the general notation for logarithms, and we'll talk about how to change an exponential function to a logarithm. And then we'll look at all the different pieces of logarithms for a moment. Right? So here's an exponential function. We have b raised to the power of x is equal to a. And if we want to transform that to a logarithmic function so that I can actually solve for x instead of using my calculator, then we can use a logarithmic function that says the log base b of a equals x. Or lots of times it's read the base b log of a is equal to x. Right? And so that's usually the way that I'll read it is, or the log of base b of a is equal to x. One of those two ways we can say it. Right? But notice the big thing is right now we're just going to work on converting. Okay? If the base for the exponential function is the base here for the logarithmic function, it's a subscript. The answer for the exponential function goes here, all right, and that's just written in the normal spot on your line, and then the exponent for the exponential function is actually what the logarithm equals. So when we find a logarithm, we're actually finding an exponent. Okay? So logarithms are basically just exponents. Okay? So we're going to do conversions. All right? So you're going to want to write this down somewhere so you can see where each of those letters go. All right? When we're converting from exponential to logarithmic form. And the first thing we're going to do, the first two examples, is one, converting from exponential to logarithmic, and then we're going to convert from logarithmic to exponential. All right, so here we have 5 exponential functions, and we're going to, or equations, and we're going to convert them to logarithmic form. All right? So first thing we'll do is we write down the logarithm, log. The base for this exponential equation is the base here, so that's a subscript. What it equals is here, and then that equals whatever the exponent is, in this case 5. All right, we'll actually have that. There we go. So log base 3 of 243 equals 5. So we write the logarithm. The base here is 25, so the base here is going to be 25. Of 5 is equal to 1/2. And the one thing to remember is that these are always true statements. Okay? They're always true statements. That the exponent, the logarithm is always equal to exponents. Your exponent's always going to be what it equals. 10 to the 4th equals 10,000. So that would be the log base 10 of 10,000 equals 4. Log base 10 of 10,000 equals 4. Fourth one here, 6 to the negative first equals 1/6. So log base 6 of 1/6 equals -1. And then log base A of C is equal to the exponent B. All right, so a big thing to remember is the exponent's always going to be what the logarithm is equal to. All right, or that this is always an exponent when we change it the other way. All right, so do these three. Write them as in logarithmic form. So when I'm checking myself on these, I like to work backwards, and for the with the logarithm, that I always think of it this way, is that b raised to that power is equal to a. So I think, b to the power of x equals a when I'm in logarithmic form. All right. So the base, what it's equal to in there. So I'm always working that direction. So if I'm checking these, all right, I think try to do it the same way. B to the power of 2, or 9 to the power of 2, does that equal 81? Yep, that's a true statement. All right, and these are always true statements, so you can check yourself by working backwards. And that's always the way I think of them with the logarithm, especially when I'm converting back from logarithmic to exponential. All right, so let's go the other way then. Here's logarithmic functions, and let's convert them to exponential. And like I said, that's the way I always think of it then, is 9 to the first power equals 9. So the base raised to the power of the exponent equals the other side. So, oops, there it is. 9 to the first power equals 9. So this one we'd say 2 to the 9th power equals 512. And 8 is my base. 2 to the 1/3 power is equal to 2. All right. And you can check these. You could take your calculator and check to make sure that you have done them correctly. And just by typing it in your calculator then, for some of them anyways, the ones you can. So here I could say, type it in, eight to the power of 1 divided by 3, and yes, that does equal 2. Okay, so it's a correct statement. Okay. 4 to the negative second equals 1/16. And here's the one thing, okay? Whenever you have a negative exponent, one of the three parts, well, let me see, if you have a negative exponent, either the base is going to be a fraction, or what it equals is going to be a fraction. So if you have anytime you have a negative exponent with working with exponentials or with logarithms, one of the other two things has to be a fraction, okay? Or a decimal, less than 1. But usually just a fraction. Because 4 squared is 16, so 4 to the negative second power would be 1/16. Okay? And the last one, b to the power of 0 equals 1. All right. So how about these three? Oops. All right. Special properties of logarithms. The log base b of b is equal to 1. All right. It's a tough one, so because if I raise b to the first power, I always get b, because any number to the first power is that number, right? Okay. And the other thing is that log base b of 1 is equal to 0, because anything to the power of 0 is 1. Okay. So we're going to look at, and then we have what's called the common logarithm. So anytime we have a base 10 logarithm, right, we're just going to write it. So if we had what they've got here, log base 10 of, of 5, right, we'll just say that's the log of 5. So anytime there is no number as a subscript here, or no base for the logarithm, that's always the common logarithm, and the base is 10. That's the one you have on your calculator. Okay? So when you look at your calculator, down here, next to the 7 key, there's the log key there. You'll notice that that's the common log, okay, for base 10. Because you notice that if the blue numbers, the blue right above it is 10 to the power of x. So those are actually the inverses of each other. We'll talk about inverses a little bit more later. But these are inverses of each other, and so they're there together with the common log and 10 raised to the power of x, right? Because they're both working with base 10. Okay. All right, so let's do a little mental math here for a moment. All right. So we're going to evaluate logarithms mentally. So we're going to test your abilities here. And remember, the thing is that when we talk about finding a logarithm, we're just looking for an exponent. Okay? And so the easiest way it might be for you is when we're trying to find an exponent, might be to just change it to exponential form to see what makes it to the true statement. So first of all, though, I would rather have a fraction here than a decimal. Okay? So this is the log of 1 over 100. So here's what we're asking ourselves then. If there's no number here, okay, so it just says the common logarithm, so that means we want to know 10 to what power is equal to 1 over 100. Right? And here's that situation we were just talking about again with, if one of them's a fraction, we know the exponent's got to be negative, okay? So 10 to what power is 100? 2, so 10 to what power is 1 over 100? And negative 2. Right? So this is negative 2. 10 to the negative second power is equal to 1 over 100, so the log of 1 over 100 is equal to negative 2. Okay. Letter B. 5 to what power is equal to 125? All right, so we're just thinking about what is the exponent that makes it true. Okay, and as Jamie said, that is a 3, because 5 cubed is 125. So all a logarithm is finding an exponent that works in that situation. So 5, here we go. We have that fraction again. So since 5 to the first power is 5, 5 to the negative first power would be 1/5. Right? So just remember that whenever one of those two is a fraction, your exponent is always going to be negative, or in this case, the logarithm is always going to be negative. Okay? So try to do these two without a calculator. And just remember that since they're written as decimals, that probably writing them as fractions first is going to help you. Yep, and that one's those are kind of tough when you have decimals. So we've got to work on them a little bit. All right? Okay, because logarithms are the inverses of exponents, the inverse of an exponential function such as y equals 2 to the x is a logarithmic function such as y equals a log base 2 of x. You may notice that the domain and range of each function are switched. The domain of y equals 2 to the x. The domain of y equals 2 to the x is all real numbers, and the range is y is greater than 0. All right, so here we have this blue graph is y equals 2 to the x. The domain, all real numbers, because I can plug in any number I want in for x and get an answer. And the range is always going to be a positive number. We talked about that on last week when we were first looking at exponential functions. So the domain of the logarithm then is going to be the x is greater than 0, and the range is going to be all real numbers. So once again, what happened? When we took the inverse, because we know when we find the inverse, we switch x and y. So if we're switching x and y, we're switching the domain and range. Okay? This is almost always the case. All right. The only time it's different than what that is right there for exponential and logarithmic is if we have a shifting, vertical or horizontal shift. Okay. Otherwise, it's always those numbers. So whenever they're talking about an exponential function or a logarithmic function, we're always talking about the domain for logarithms, x is greater than 0. The range is all real numbers. Okay? So for what we're doing for today and just about this whole rest of this chapter, when we're talking about domain and range for logarithms, almost always, if it's working with a function, the domain is x is greater than 0. The range is all real numbers. All the time. When we're talking about a function. Okay? So you can look at, here's the graph of y equals log base 2 of x. All right? Starts at the y-axis and goes to the right. All right. So here we have f of x equals 1.25 to the power of x. All right. And here I've already put these numbers in the table for us. Negative 2 to 2 for our x's, and our y values when we plug them in. And just like when we were graphing inverses on Friday, to graph these inverses we do the same thing. We just switch x and y. So here's the graph of y equals 1.25 to the power of x. So the graph of the inverse then, so we graph the inverse, we've got the 0.64, negative 2. So my x value is 0.64, my y value is negative 2. So that's going to be about here. 0.8, negative 1, about there. 1, 0. These 2 points, all right, if you have an exponential, if you have a logarithm, those two are going to be there unless we have some value of a in front, okay? So most of the time, those are there. We have 0, 1 and 1, 0. Right? 1.251 and 1.562. Right? So the graph of the logarithm then will look like this. Eventually it will go this way. So if you notice, this graph of the logarithm goes up and curves to the right, correct? The graph of the exponential is, as it goes to the right, it's curving up. Right? What's going to happen with those two graphs? They're going to intersect. Where are they going to intersect? On the line y equals x. Okay, they're going to intersect where the x and y are the same number. Okay, they intersect here at where x and y are the same number, and they're going to intersect over here again. So they're actually going to cross each other twice, but they're going to cross each other at the line y equals x. So if we write this exponential function then, or logarithmic function, it's going to be that f of x equals the log, and what's the base? 1.25 of x. So there's our exponential function. All right? So what's the domain? No, the domain is exactly what they said it was up here. X is greater than 0. The range is all real numbers. When we're talking about functions, these are the domain and range always. If my exponential function is 1.25 dx, my logarithm is a log base 1.25 of x. Okay, let's look at another one. F of x equals 1/2 raised to the power of x. All right, so 1/2 to the power of -2. What do we do when we have a negative exponent? Take the reciprocal. All right, so what's 2 to the power of +2? 4. I don't want that. All right, I guess it's not going to cooperate with me. All right, so this is 4 here. Okay, so this would be 1/2 to the negative first power, which is 2 to the first power, or 2. Zero, or 1/2 to the power of 0, anything that has the exponent of 0 is always going to be 1. And we get 1/2 and 1/4. 1/2 to the first power is 1/2, 1/2 to the second power is 1/4. Okay, so we plot those points. So -2, 4, -1, 2, 0, 1, 1.5, and 2 and 1/4. All right, so that's y equals 0.5 to the power of x. Let's see if this will cooperate with me today. Infinite, I guess not. All right, so goodbye. All right, so we graph that. And the graph looks like this. All right, never crosses the x-axis. So we do the inverse. All right, so we're just switching x and y again. All right, so we have 4, -2. 2, -1. 1, 0. 1/2 1, and 1/4 2. So this graph then is going to look like this. Now this one's only going to cross in one place, and that's still going to be through the line y equals x, right? And so this is y equals the log base 1/2 of x. All right, just make sure that that 1/2 is always, you're writing that as a subscript. And the domain is still, if we look at this, all the x values to the right of 0. The range goes to positive infinity to negative infinity. So domain x is greater than 0. The range, all real numbers. And the only time that will ever change is if they ask you to do, they say, hey, use these numbers. But if it restricts everything to just these numbers, okay, and doesn't say it's a function, then, okay, then it's not all real numbers. Just depends on your values of x and y that you get.